Here in this video we look at unloading a shift register, which is getting data out of the register. Previous video we saw how you were to load a shift register, and remember that when loading a shift register you're performing a serial to parallel data conversion. You'll see when you unload a shift register you're doing the opposite. You're performing a parallel to serial data conversion. So if you're unloading a shift register, that means it's previously been loaded. So the initial state here is that you have some data that has been loaded. So I'm using an example of a 1010 where if Q0 was our most significant bit, if that was our most significant bit flip-flop determined by the designer, you know, this would be a binary 10. So this binary 10 was loaded previously, and now we're going to unload it from the shift register. So initially when you're unloading, the clock and the serial input are don't cares, and in fact during the entire time you're unloading, the serial inputs are don't care. Okay, because when you're unloading, the serial input doesn't have any relevance. It only has relevance when you're loading. So to unload, you just simply clock the register. So again, going with the same example we had in the previous video with the negative edge register, okay, a register that has negative edge trigger Ds. At the time of the 1 to 0 transition, well, the bits are going to shift over one place. So Q3 will equal Q2, so this 1 comes over here, and then Q2 equals Q1, so that 0 comes here. Q1 equals Q0. So that 1 comes here, and then the don't care comes into the register at Q0. Okay, so we clock it a second time, and after that second clock pulse, we would have 0, 1, don't care, don't care. Again, we make that a don't care. That's what we're, again, since we're unloading, we don't care what we're inputting at the serial input. And then you would just need one more clock pulse to finish this off, because after that third clock pulse, if you look right here at Q3, which is your serial output, okay, if you look back at the diagram, Q3 was our serial output. Well, here's that same 1010 that initially was in the register, and now it's available at the serial output. So you see, when you unload, you're going the opposite direction as when you're loading. When you're loading, you're going serial to parallel. When you're unloading, you're going parallel to serial, because that serial output is just going to be one wire that had the data displaced in time, right? 0, 1, 0, 1, and before it was unloaded, it was all in parallel, right, where you had your outputs Q0, Q1, Q2, Q3. So 1, 0, 1, 0. Okay, now you can see here sometimes students ask, well, isn't this 0, 1, 0, 1? Well, it depends what you take as the most significant bit. So the designer would make sure that this first pulse that came out, that was the most significant bit, right? This is our most significant bit here. Well, we'd make sure that in our design we take this first pulse on our serial line, our serial output line, as the most significant bit. Alright, that wraps up shift registers. Now there are also memory registers, and the difference between shift registers and memory registers, one, as you'll see in a moment, is how the flip-flops in the registers are connected. Remember, the flip-flops in a shift register are connected in cascade fashion. For a memory register, the flip-flops are connected as you see in this diagram, where you don't have a cascade connection. See, the output of the flip-flops are not connected to the D inputs of the other flip-flops that make up the register. In fact, these D inputs and Q outputs of the memory register are what are called standalone. that the D inputs don't connect to any other part of a flip-flop that's in the register, and the Q outputs also do not connect to another flip-flop that's makes up the register. But just like the shift registers, memory registers are synchronized. Their clock inputs are connected together. So let's see how this memory register works by doing an example of putting data into a memory register. So here this is, loading a memory register, putting data in. Alright, so let's say that just like the first example with the shift register, we loaded in a binary 6. So let's say that's what we want to load into this memory register. Well, the way you would load in a binary 6 is that initially, you'd put the binary 6 there. And initially we don't care what the outputs are equal to. They're going to be zeros and ones here, but before loading we don't care what they are. Well, to load a memory register, all you have to do is provide one clock pulse. Now, let's be careful here. Let's look at the diagram. These are actually positive edge trigger Ds. Okay, so we need a 0 to 1 transition, so I almost made a mistake there. Okay, so on the 0 to 1 transition, okay, at the time that this 0 to 1 transition occurs, well, the output of each edge trigger D is going to equal its D input. So you see Q3 equals D3, Q2 equals D2, Q1 equals D1, Q0 equals D0. So our outputs are going to stay 0, 1, 1, 0, and at the time of that 0 to 1 clock transition, Q3 equals D3, makes it a 0, Q2 equals D2, which is a 1, Q1 equals D1, which is a 1, Q0 equals D0, which is a 0. So here's a fundamental difference between loading a memory register and loading a shift register. Well, when you load a memory register, it only takes one clock pulse to load it, and that doesn't and that's regardless of how many bits you're loading. If this was an 8-bit register, 8-bit memory register, we'd have 8 edge trigger Ds connected the same way as this 4-bit, and it would still just take one clock pulse to load all 8 bits. If it was a 64-bit memory register, again, it would only take one clock pulse to load it. Now, if you have a 64-bit shift register, it's going to take 64 clock pulses because it takes a bit or a clock pulse per bit that you load, as we saw in the previous video. Alright, so now the reason why this is called a memory register is now, and this is its primary purpose, is now if we don't receive any clock pulses, well, the D inputs could be changing as much as you want. Like this could change to a binary 9, and if we haven't had any clock pulse, okay, if the clock line has just been low, to be clear here, it's just a 0 or it's just a high, as long as it's not a 0 to 1 transition, well, the output of that memory register is just going to stay with the previous data. It's going to store that binary 6. So the D inputs could be changing as much as you want, and as long as there's no, let's make sure this is clear here. Let's okay. Yeah, so as long as there's no there's no 0 to 1 transition, the output of the memory register is just going to stay with its previous data. So that's the primary purpose of a memory register, and that's why it's called memory, is that it's remembering or retaining data from a previous time. The only way to change the data that's loaded into a memory register is to provide a 0 to 1 clock transition, with a different data on the D inputs. Okay, now a shift register, it's called a shift register because, as we saw, and its primary purpose is to manipulate data by shifting the bits around. it can also store data, but it has that unique ability to shift the bits around and change what data you have. Alright, well that wraps up information on registers. We will talk in the next video about memory ICs, some of the basics of memory ICs.